Now, so let's look at the last method that we want to look at under limits of rational function. So we solve using the direct substitution, we solve using the factorization method, and we also solve using the substitution method, which is also called the change of variable. Now we want to look at limits of certain forms that we call the standard forms. Now, if limits of rational function are in this form, a base raised to a power minus another base raised to the same power. The same power here is the same power on this side. And then down here you have the same bases that are within the numerator, but now will actually be raised to the same power or to different power. But the powers down here must be the same. Now, so we said this is now equal to n, the power of the numerator, divided by the power of the denominator, which is just 1, times the term that is attached to the negative, a raised to the power of the numerator minus the power of the denominator. So we want to prove that using the binomial expansion. Now we know that the general form for the binomial expansion for in this form x to the power n minus a to the power n is just equals to x minus a times x to the power n minus 1, a raised to the 0 power, plus x to the power n minus 2, just like that, a raised to the first power, n minus 3, a raised to the second power, continuously until you reach to the last one. So how do I know that I've reached to the last one? You see this one, you see this term, and you see this one? These are the last terms. Now, the highest power right here cannot be the highest power right here. It will drop by 1 because we have already extracted 1 from here. So that's the reason why you see n minus 1 to be the first term here and n minus 1 to be the first term at the end. Let's prove it. Let's try something, right? What if we had x raised to the third power, right? Minus y raised to the third power. So let's say a raised to the third power. So this is now equals x minus e, right? Times x now raised to the power 3 minus 1. This is the first one, right? Plus x now raised to the power 3 minus 2. This is just 2. The power is 2. Yeah, the power is 1, right? Then the next one now you have, if I in the same term, you have a now going to the first power plus. Now what you should observe is that whenever you have cubic function, right? Whenever you have cubic function, you will have like 3 terms in it. 3 terms. So when it is a kind of square, you have 2 terms in it. When it is raised to the 4th power, you have 4 terms in it, just like that. So now the next one now will be, which will be the last term, we just have x raised to the power 3 minus 3. So even if you were not told as to how many terms you will have, as long as you have the first term that started with the power 3 minus 1, as long as it reaches 3 minus 3, or if it started with 4 minus 1, as long as it reaches 4 minus 4, which is now being raised to the 0 power, that's the ending point. So this is now a raised to the power just 2. So let's simplify it. You have x minus a times x squared plus x to the first power a plus x to the 0 power now is just equal to 1. Then you have a squared. So you see that? That's the binomial expansion. So now let's go ahead now by proving this thing. So we take the limit x minus x to the power n minus a to the power n is just this expansion, right? So we replace it now with x minus a times x to the power n minus 1 plus x to the power n minus 2a plus x to the power n minus 3a squared plus x to the power n minus 4a cubed dot 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 all the way a raised to the power n minus 1. All divided by the denominator here now is just x minus a, right? So as x approaches a, so what you observe is that x minus a and x minus a will go out. So because there is nothing now within this expression that is taking this entire denominator to 0, because this denominator has been cancelled, we can now apply the limit. So if you apply the limit now, you will have, wherever you see x, you put a. So here now is a raised to the power n minus 1 plus a raised to the power n minus 2 times a plus a raised to the power n minus 3 times a squared plus a raised to the power n minus 4 times a cubed plus dot 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 a raised to the power n minus 1. So let's simplify. The first one is n minus 1 plus, now the power here is 1, right? So it's like saying n minus 2 plus 1 because we add in the power. So it will just be n minus 1. Plus the same thing, you add in these two powers, so it will just be n minus 1. So you understand that it will just be the same thing. This will also be, if you add this, negative 4 plus 3, it will be a raised to the power n minus 1. Plus dot 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 a raised to the power n minus 1. So if you observe this thing, a raised to the power n minus 1 has been expressed n number of times. Infinitely many times, right? N number of times. So because a raised to the power a now raised to the power n minus 1 has been expressed n times, so we just say n a raised to the power n minus 1. So it was how we got n a raised to the power n minus 1. But now, what if this denominator, the power is not 1? What if the power is 2? Or the power is 3? Or the power is 4? Or the power could just be any different expression, right? But remember now, the two of them will be the same. So generally, we could say the standard limit could be of the form x raised to the power m minus a raised to the power m all over x to the power n minus a to the power n as x approaches a. Could just be equals to the power of the numerator divided by the power of the denominator times a now raised to the power m minus n. So this is just a general form for the whole thing. Instead of using this form wherein it only works whenever the power of the denominator is equals to 1. Now let's look at the first batch of examples. It's on the standard limit. Now find each limit of the, let's say find each limit if they exist, right? Meaning if the value of the limit is equal, it's actually accepted. Like for instance, it's not an undefined statement. That's exactly what we were asked to do. To find each limit if they exist. If they do not exist, it means that you will have either like 0 in the denominator that will make the problem to be undefined or be infinitive. Now, so we do the first problem. The first problem says that we must be able to simplify, or let's say find the limit of x cubed minus 1 divided by x minus 1 as x approaches 1. Now let's go the long method so that you can see something. Let's use the factorization method. Factorize. Now, To factorize this, remember now you have x cubed, 1 cube, right? And then 1 cube. So it's similar to what we have, x cubed minus y cubed, that expansion. So the numerator now will be x minus 1 times x squared plus x times 1 plus 1 squared, right? Divided by x, the same thing down here. In fact, this is just x minus 1, right? So there is no cube to it. So we just have x minus 1 as x now approaches 1. So what happens? What do you observe? You observe that x minus 1 and x minus 1 will go out. You'll be left with the limit of x squared plus x plus 1. As x now approaches 1, what will you have? You apply the limit, you have 1 squared plus 1 is just equals to 3. But let's go the other way. If you have the limit of x cubed minus 1 cube all over x minus 1, as x now is approaching 1. So, observe, are the bases the same in both the numerator and the denominator? Yes. Here is x, here is x, here is 1, there is 1, right? Now, are the powers the same within the numerator? You have 3, yes, the powers are the same in the numerator. Are the powers the same in the denominator? Yes, here is 1, here is 1. Do we have negative in both the numerator and denominator? Yes. So those are all of the basic questions that you must first answer. So after answering those questions now, then you apply the standard limit. So you see the power of the numerator, 3, divided by the power of the denominator, 1, times the term that is attached to the negative, right? 1, raised to the power of the numerator minus the power of the denominator. So therefore, you just have 3. 1 raised to any power is just equals to 1. 3 times 1 is just 3. So you see that? So this is how faster, it works when you are dealing with the standard limit. Now question 2, you have x to the third power minus 8 divided by x minus 2. So we apply the standard limit, but we observe that this one is not the same as the base down here. So we can make it to be the same as the base. So we have x to the third power minus, we know that 2 raised to the third power is equals to 8. All divided by x to the first power minus 2 raised to the first power, right? As x approaches 2. So now, it is okay that the numerator bases are equal to the denominator bases. Secondly, the powers in the numerator are the same, and the powers in the denominator are also the same. So we can just say now, the power of the numerator, which is 3, divided by the power of the denominator, which is 1, times 2 now, raised to the power of the numerator minus the power of the denominator. So the same thing that will be here, it is just the same thing you're writing on this side. So you have 3 now times 2. 3 minus 1 is just equals to 2. 2 times 2 is 4. 4 times 3 is 12. So if we are to apply the factorization method on this problem, it will still give you the same thing. We are not going to apply the factorization on all of them. So from this area now, you will have the limit. So you bring in x cubed minus 2 cubed. So it's this one. You bring in that expansion, x minus 2 times x squared plus 2x plus 2 squared. All over x minus 2. So x minus 2 and x minus 2 will go out. So you just be left with the limit of x squared plus 2x plus 4 as x approaches 2. So you apply the limit, now you have 2 squared plus 2 times 2 plus 4. So this is 4 plus 4 plus 4. 4 times 3 is 12. That's how we got it 12. So because 12 now is a real number, 12 is not undefined, the limit exists as x is approaching 2. Now, one reason why the standard limit is important is because at times you may have problems in this form that may appear difficult to be factorized. So you just be ready in the standard form and be able to express it in this form so that you get your final answer. So you don't strive factorizing a problem, when you already have a simple way of deriving at the answer. So now, in this one now, we will not strive in showing that we factorize this expression, right? So what we can do is to make the base here to be the same as probably a number that will be raised to 5, if that is possible. So let's say we try 2, right? So 2 times 2 times 2 times 2 times 2. This is 4, this is 4, and this is 2, right? So this is 4 times 4 is 16 times 2. 16 times 2 is 32. So we know that 2 multiplied by itself 5 times, which can also be expressed as 2 raised to the 5th power, is equals to 32. So we can now safely say x to the 5th power minus 2 to the 5th power. Then we come down here. X to the 3rd power. So there is just a hint. X to the 3rd power. So we need to look for a base that we can multiply 3 times to give us 8. And we must be guided by the base within the numerator. So since the base in the numerator is 2, we say let's try 2. So 2 raised to the 3rd power now is equals to 8. So we have 2 raised to the 3rd power as x is approaching positive 2. So finally, we can just have our answer now to be the power of the numerator divided by the power of the denominator, right? Times the term that is attached to the negative 2 raised to the power 5 minus the power of the denominator 3. So if you are writing this 2, you don't carry this negative any longer. So this is 5 over 3 times 2 raised to the power 5 minus 3 now is 2. So this is 4. So you have 5 over 3 times 4. So 5 times 4 now is just equals to 20 all over 3. So our final answer now is 20 over 3. So the next one now, we do the same thing. This is already 2 in the denominator. So we think of how we can make this base here to also be 2 raised to this power, which is 7. So 2 times 2 times 2 times 2 times 2 times 2 times 2. So this is now 4, this is 4, this is 4, and this is 2, right? This is 16, and this is 8. So it's like 8 times 16, right? So 8 times 6 now is 48. 8 times 1, 8 plus 4 is 12. So it's 128. So it means that we can have 2 raised to the 7th power to give us 128. So we can rewrite this thing as the limit of x to the 7th power minus 2 to the 7th power all over x minus 2 as x is approaching 2. So finally, we're going to say 7 over 1 times 2 raised to the power 7 minus 1. This is just 7 times 2 raised to the 6th power, right? So we have 7 times 2 times 2 times 2 times 2 times 2 times 2. 2, 4, 6. So this is now 4, this is 4, this is 4. This is 16 times 4. So 16 times 4, you have 16 plus 16 is 32, times 2 now is 64. So it's 7 times 64. 7 times 4 is 28. We carry the 2. And then 7 times 6 is 42. And then plus this 2 now is 44. So we have 448. So now we have another one. So the first thing we can do, we write it in the form of exponent. So this is x raised to the power 1 over 3 minus 1, all divided by x raised to the power 1 over 2 minus 1, as x is approaching 1. So now, do you know that 1 can be raised to any power and it's still 1? So we can raise this 1 to 1 over 3. Meaning the cube root of 1 is just equals to 1. The fourth root of 1 is 1. The square root of 1 is 1. So we can also say 1 raised to the power 1 over 2. So since the bases in the numerator and the denominator are the same, you got minus sign between them. The powers up here are the same. The powers down here are also the same. So we can now say the power of the numerator, which is 1 over 3, divided by the power of the denominator, which is now 1 over 2, times 1 now raised to the power 1 over 3 minus 1 over 2. So this is now a complex fraction. You have 1 over 3 divided by 1 over 2. Now 1 raised to any power is just equal to 1. Don't give yourself tough time to say you find the LCD and after that, no. It will be equals to 1. So the division here now, we can say multiplication and we reciprocate this one, meaning we send this 2 above. So it's 2 now over 1. So our final answer will just be 2 over 3. So the next one is x to the 9th power minus x to the 4th power, x to the 9th power, let's say 4 to the 9th power again. So the bases are the same, both up and down, and the powers are the same in the numerator. The powers in the denominator are also the same. You got 1, 1. So it's just easy now. You can just say 9 over 1 times 4 raised to the power 9 minus 1. It's just very easy. So this is now 9 times 4 to the 8th power, which is 4 times 4 times 4 times 4 times 4 times 4 times 4 and times 4. There's 4, there's 4. So it's 9 times 4 times 4 is 16 times 16 times 16 and times 16. 589,824 as our final answer. Now let's solve another set of examples that are in different form, right? So the first one says, if the limit of x to the power n minus 2 to the power n divided by x minus 2 raised, let's say all equals now to 80 as x is approaching 2, find the value of n. Now remember, we do not know this value n. We do not know n, but we know the rest of the other ones. So the first thing we can do is to write it in this form. So you have the limit of x to the power n minus 2 to the power n all over x minus 2 as x is approaching 2 all equals to 80. So we write this one. You have the power of the numerator divided by the power of the denominator, which is 1 now, times 2 raised to the power n minus 1. All must be equals to 30. Now we have an exponential function to find the value of n. Now you have n times 2 raised to the power n minus 1 all equals to 80. It's 80, not 80 degrees. Now, so what we need to do with this 80 is to open this 80 up, right? To find the factors of 80. So we first start with 2, because we know that 80 can be divided into 2. So when 80 is divided into 2, it's 40 times, right? It's 40, 40. So you have 2 times 40 give you 80. Again, divide this 40 into 2. So you have 2 times 20 give you 40. Again, divide this 20 into 2. You have 2 times 10 give you 20. Again, divide this 10 into 2. You have 2 times 5 give you 10. Right? Now, take all of these like numbers. So you have like n times 2 n minus 1 equals. So all of these ones, put them together. There is 2 raised to the power 4, right? 1, 2, 3, 4. Excellent. And then it's just 5. So we can say 5 times 2 raised to the power 4. Now I wrote this 5 first so that we can pair the 5 and this n, because the 5 and this n does not have power, right? The power here is just 1. But this one, it has power that is more than 1. So we can pair the first factor, this factor, and this one, right? So we equate n and 5. So we have n is equals to 5. Let's prove it as whether it is equal to 5 in the next factor. You have 2 raised to the power n minus 1 equals to 2 raised to the power 4. Now when the bases are the same in exponential function, we get rid of them and equate their power. So it's n minus 1 is equals to 4. So n now is equal, you send this 1 across, is 4 plus 1, which would now give us n equals to 5. So we now know that the value of n is 5. Is it true? Let's prove it. If you put 5 right here, let's take 5 and replace 5 with n. We put 5 here and say we don't know this 80. So this is now 5 over n, which is, let's say 5 over 1 times 2 raised to the power 5 minus 1. So it's just 5 times 5 minus 1 is 4, so it's 2 times 2 times 2 times 2. 2 times 2 is 4, 2 times 2 is 4. 4 times 4 is 16. 16 times 5. 5 times 6 is 30, you carry the 3. 5 times 1 is 5 plus 3 is 8. So our answer is correct. Let's do the next problem. Next problem says, if the limit of x cubed minus a cubed divided by x minus a equals to the limit of x to the 4th power minus 1 divided by x minus 1, find all values of the variable a. So we can individually simplify these limits and solve for a. So remember using the standard limit now, because in the standard limit form, we have the power of the numerator 3 divided by the denominator's power, which is 1. Here is 1, times a raised to 3 minus 1 equals the same thing on this side. Now this 1 can be raised to the 4th power, is the same 1. It is not negative 1 that is going to be raised to the 4th power, no. It's just positive 1 that is going to be raised to the 4th power. So we have 4 over 1 times 1 now raised to the power 4 minus 1, because the power down is 1. So this is now 3a raised to the 2nd power equals 4. Now, if we look here, 1 raised to any power, like I told you, it just equals to 1, right? So this is just 4. We want to now solve for a. So we use the square root method. So we take the square root on this side and take the square root on this side. So we can now take the square root of 3. We can also take the square root of a squared. This one is the same as saying 2 raised to the 2nd power. So you see that? So this can cancel this 2. This can cancel. But the 3, it still remains as it is. So we just have the root of 3 times a is equal to plus or minus positive 2. We want to solve for a. We divide this out by the root of 3, and we also divide this out by the root of 3. So therefore, we will have 3 will go out. You just have a now to be equal to plus or minus 2 all over the root of 3. This plus or minus means a value can be 2 over the root of 3, or a value can be minus 2 over the root of 3. But what if we don't want to use root of 3 in the denominator? We can rationalize this root of 3. Rationalize means we multiply root of 3 both in the numerator and the denominator. So this will give us plus or minus 2 times the root of 3. We can now multiply 2 by 3 because this 2 does not have a root. If it had a root, we would have multiplied the 2 of them. Now the square root of 3 times the square root of 3, you see we can multiply the 2 of them. 3 times 3 is 9. and the square root of 9 is just equal to 3. So therefore, that whole thing would just be 2 the root of 3 divided by 3, and then minus 2 the root of 3 also divided by 3. So those are the values of A that we were asked to find. Now let's do the next one. Now this one says the limit of x plus 2 raised to the power 3 over 2 minus a plus 2 raised to the power 3 over 2 divided by x minus a. Now, we observe that the base in the numerator, they are all being raised to the same power. That is correct. There's a minus sign between them. It is also correct. But let's look within the denominator. The base right here, is it the same base here? No. This base, is it the same base here? No. But observe something. Do you know that x plus this 2 minus a plus this 2, right? If you simplify it, x plus 2 minus a minus 2, 2 carry 2 out. It's just equal to x minus a, which is the denominator. So do you know that this x plus 2 plus, that's a minus a plus 2 can just be equal to x minus a. So it means wherever we see x minus a, we put x plus 2 minus a plus 2. The main reason of doing this is to ensure that the same basis up here should be the same basis within the denominator. So now we have the limit now of x plus 2 raised to the power 3 over 2 minus a plus 2 raised to the power 3 over 2 all over. Now this now is just equal to x plus 2 minus a plus 2. Now all of these raised to the first power. You see that? So the bases now are the same. The powers in the numerator are the same. The powers in the denominator are the same. We can now apply the standard limit. So we see the power of the numerator, 3 over 2, divided by the power of the denominator, which is just 1, times a plus 2, the term that has the negative attached to it, raised to the power 3 over 2 minus 1. So this 3 over 2 divided by 1 is the same as 3 over 2. This is a plus 2. Now, 2 times 1 is 2, right? So it's like 3 minus 2 all over 2. Because if you want to find the LCD, you can say the LCD now is 2. 2 into 2, 1 times 3 is 3, minus 1 into 2, 2 times 1 is 2. Or you can just say 2 times 1 minus 2 straight. Minus 2 now plus 3, it will give you positive 1. So this is just 3 over 2 times a plus 2 all raised to the power 1 over 2. Or we know that the square root, whenever you see the power of a particular expression is half, it means that is the square root of that expression. So with 3 over 2 now, you have the square root of a plus 2 as our final answer. The same thing we got it. 3 over 2 a plus 2. Now let's solve question 11. Not question 11, but question 10. So question 10 is similar to question 7, right? To find the value of n. So we do the same thing. The power down here, remember 1, 1. So we say the power of the numerator divided by the power of the denominator times 3 raised to the power n minus 1, all equals to 108. So this is now n times 3 raised to the power n minus 1, all equals to 108. Now this 108, we can find the prime factorization of 108. So now 2 times, if you divide this 108 into 2 is 54. This again, you divide this 54 into 2, it gives you 27. 27 cannot be evenly divided by 2, but 27, you can have 3 times 9, 27. And then this 9, you can have 3 times 3, right? So now what are those expressions that we have? We have 2 times 2 times 3 times 3 times 3. So this one is 2 to the second power times 3 to the third power. So it's 2 to the second power times 3 to the third power. We cannot pair this first one and this one because the base here is 3. So we can pair it with the one that the base is 3. So now it's n equals to 2 squared or 3 raised to the power n minus 1 equals to 3 to the third power. So what happens? This cancel. You have n minus 1 is equals to 3. N now is equals to 3 plus 1. N is equals to 4. And then this side n is also equals to 4. Mathematics make simple. Mathematics makes simple. Very, very easy. Math is never difficult. It depends on how you approach the math, or it depends on how your instructor fears the math. So we have the next problem, question 11 now. Question 11 says that if the limit of x to the 9th power minus a to the 9th power divided by x minus a as x approaches a was equal to 9, then what is the value of a? What are all positive values of a? And so the answer is plus or minus 1. So let's find it. So now this portion is in standard form, so we can rewrite it as the power of the numerator divided by the denominator's power times a raised to the power 9 minus 1. So this is just equal to 9. Right? So now we have 9 times a raised to the 8th power is equal to 9. So what do? We divide this out by 9 and divide this out by 9. So what will we have? We will have a raised to the 8th power equals to 1. So a raised to the 8th power now equals to 1. We need to get rid of 8. So we can take the 8th root on both sides. We take the 8th root on both sides. So you have the 8th root cancelling this room. So you have now a to be equals, because it is an even root, this is even, so you will have plus or minus at the end. If it was odd, you would not have plus or minus. Because this is to say that you have something like 1 square, positive 1 square, or minus 1 square. All raised to the 4th power is the same, right? Or even you can say 1 square, let's say 1 raised to the 8th power, and then negative 1 raised to the 8th power. 1 times 1 times 1 times 1 times 1, all to the 8th power now is just 1. The same thing, negative 1 raised to the 8th power is also positive 1. So either of them, if you raise it to the 8th power, it will give you positive 1. Right? So you can now safely say that what are those things that will give you positive 1 is either 1 to the 8th power or negative 1 to the 8th power. So this now you have plus or minus 1. Because this is just 1 to the 8th power, right? Plus 1 to the 8th power will give you 1. Minus 1 to the 8th power will also give you 1. So that's the reason why we have plus or minus 1 as our answer. So it's just simple. Take 1 and put 1 here. You put 1 here, right? Replace this one with positive 1. Positive 1. And then this will just be 9 over 1 times 1 now raised to the power 9 minus 1. 1 raised to any power is just the same as 1. So this just equals to 9. What if this one was minus 1 raised to the 9th power divided by minus 1 raised to the first power? Right? It's the same thing. So you will have minus 1, right? Minus 1 raised to the power 9 minus 1. So 9 minus 1 now is 8. Negative 1 raised to the 8th power is positive 1. Times this 9, it gives you 9. So either of them you use, they will still be the same. So now we have these will be supplementary problems. So what I'm going to do, I'm just going to solve one from there, and then the rest of them now you can practice. So like I said, I'm going to solve only one. So I'm looking at 16 or 17. So let's say I solve 17. 17, we have the limit of x to the power 2 over 3 minus a to the power 2 over 3 divided by x to the power 3 over 4 minus a raised to the power 3 over 4 as x approaches e. So the bases are the same, the powers up here are the same, and the powers down here are the same, right? So now we can now use the standard limit. So we have the power of the numerator 2 over 3 divided by the denominator's power 3 over 4 times a raised to the power 2 over 3 minus 3 over 4. So this is 2 over 3 divide 3 over 4 times a raised to the power, now the LCD for that is 12. 3 into 12, it goes there. 4 times 2 is now 8. 4 into 12 goes there. 3 times 3 is 9. Right? So we will have 2 now over 3 times 4 over 3. So this is now a raised to the power 8 minus 1. 8 minus 9 is just minus 1 over 12. So this is 12, not just 2 over 12. And then 2 times 4 is 8. And then this 3 times 3 is 9. So this is a raised to the power negative 1 over 12. So if the answer is negative 1 over 12, you can maintain it. If you don't want the answer to be negative, you can now rewrite it as 8 over 9 a raised to the power positive 1 over 12. Because if you send this expression within the denominator, the power changes from negative to positive or from positive to negative. So that is our final answer. So the rest of them now you can practice.